Physics, CXC revision, speedrun. Let's go. A base or fundamental quantity is one that cannot be expressed as another quantity. Example, length, time. A derived quantity is one that is a combination of base quantities. Example, speed is distance per unit time. Here we have the 7 base quantities. You only have to know 5 at this level. The 5 are length, which is the unit is meters, mass, the unit is kilograms, time, the unit is seconds, current, the unit is amperes, and temperature, the unit is Kelvin. The other 2 are the amount of a substance, the unit is moles, and luminous intensity, which the unit is candelas. These are a few derived quantities. We have area, the unit is meter squared or meter by meter. Volume, the unit is meter cubed or meter by meter by meter. Pressure, the unit is pascals or newton per meter squared. Force, the unit is newtons or kilogram meter per second squared. And charge, the unit is a coulomb, which is an ampere second. There are many prefixes, but these are the 5 that you have to know at CXC level. We have micro, milli, centi, kilo, and mega. Micro is 10 to the power negative 6, basically means divide by a million. Milli is 10 to the power negative 3, which means divide by 1,000. Centi is 10 to the power negative 2, which means divide by 100. Kilo is 10 to the power 3, which means multiply by 1,000. Mega is 10 to the power 6, which means multiply by a million. Here are a few examples of how to convert SI unit. 5600 milliseconds to seconds. Milli means divided by 1,000, so 5600 divided by 1,000 is 5.6 seconds. 300 centimeters to meters. 300 divided by 100 is 3 meters. 2.5 kilowatts to watts. 2.5 times 1,000 is 2,500 watts. Scalar is a quantity that has magnitude but no direction. Vector is a quantity that has both magnitude and direction. Examples of scalars would be distance, speed, area, volume, and density. All of these would have magnitude but no direction. Examples of vectors are displacement, velocity, acceleration, force, and momentum. All of these would have magnitude and an associated direction. If you have 2 vectors that are aligned or parallel or anti-parallel, on the one to the left, we can see 5 newtons and 5 newtons are heading in the same direction. The product of these would just be the sum. 5 plus 5 is equal to 10 newtons. On the diagram to the right, we have 4 newtons heading to the right, 20 newtons heading to the left. The net force of this would be the difference between these 2 vectors, which would be 20 minus 4, which is 16, because they are heading in opposite directions. In order to resolve non-parallel vectors, if we look on the one on the left, if both vectors are at a right angle to each other, we can simply use Pythagoras' theorem to resolve the resultant. So for example, the 2 vectors, force 1 will be A, force 2 would be B, and the resultant would be C. If you use A squared plus B squared equals C squared, and A is 3, 3 squared is 9, and B is 4, 4 squared is 16, 9 plus 16 is equal to C squared. So C squared is equal to 25. C would be the square root of 25, which would be 5. So the resultant would be 5 units in this case. If they are not at a right angle, you would have to draw the 2 vectors, decide a scale, complete the figure into a parallelogram, and then to find the resultant, you draw a line from the origin of these 2 vectors to the other end of the parallelogram. Using your scale now, measure the resultant and convert the units. Mass, which the unit is kilograms, is the amount of matter contained in an object. It is a measure of an object's inertia or resistance to change in motion. Basically, objects that have more mass resist changes in motion more. Weight is measured in newtons. Weight is a force exerted on a body's mass by gravity. The formula for weight is given as W is equal to mg, where m is mass and g is acceleration due to gravity. An example question: if an astronaut has a mass of 70 kilograms on Earth, what is her weight on the moon if its gravitational field strength is 1.6 newton per kilogram? The mass is 70, g is 1.6, multiply the 2, you get 112 newtons. This will be her weight on the moon, but her mass on the moon would actually stay as 70 kilograms. The center of gravity of an object can be defined as the point at which the weight of a body acts, basically where the object will balance. Here we can see 3 situations. The first one is stable equilibrium. This is when the center of gravity is low or the base is wide. Unstable equilibrium is where the center of gravity is high or the base is narrow. And neutral equilibrium is where when the object moves, the center of gravity doesn't change. So the wide base or low center of gravity means a higher stability. Forces enable masses to overcome inertia. That is, they are able to cause a change in an object's acceleration, deceleration, or direction. They can even cause deformity, causing changes in shape and size, but they will never change the mass of an object. Forces are measured in newtons, and newtons can be derived as kilogram meter per second squared. Basically, mass times acceleration. Here we have a table with a number of forces. I would advise to pause the video and take note of the description shown. You should be able to describe at least 4 of these forces here, but be able to recognize all. If a force is absent, there will be no change in motion or direction. In this diagram to the right, the 2 resistant forces on the car, 500 and 700, the sum of that is 1200. And since the thrust is also 1200 forward, that means if you was to add all the vectors together, you will get a net force of 0. This does not mean that the car will stop. It means that the car is at equilibrium and the car will keep moving at a constant velocity. Now remember, no force means no change in motion. It will keep doing what it was doing before. In a vacuum, objects, whether it be a rock, paper, or even a car, will accelerate and fall at the same rate in a vacuum because there's no air. In air, however, the force of air resistance will affect falling speeds. As you can see on the figure on the left, where there's air particles, the piece of paper falls a lot more slowly because of its wider surface area and more contact with the air molecules. The acceleration due to gravity on Earth, or g, is given as 10 meters per second squared unless otherwise. This means that with each second under the force of only gravity, velocity increases by 10 meters per second. So 10 meters per second squared basically means 10 meters per second. So that means after 3 seconds in free fall with negligible air resistance, the final velocity would be 30 meters per second. Here we have a diagram showing 4 stages of a parachuter falling. On the first stage here, we have the parachuter falling without his parachute, and thus he is accelerating due to gravity. This is because his gravitational force is higher than his air resistance. When he does pull the parachute here in the second diagram, we can see that the air resistance increases suddenly, but his gravitational force remains the same. This means that he will decelerate in mid-air, not go upwards. On the third diagram, we can see that the air resistance is now equal to the gravitational force. Once again, this does not mean he will stop, it just means he will stop accelerating or decelerating. Thus, he will be at a constant speed or a terminal velocity. He will not go any faster than how he's going now, unless something were to happen to the parachute. Finally, it shows that the parachute has landed. When he has landed on the ground is going to exert a reaction force upwards to decelerate and stop him. Then he's going to remain at rest. The action force of his weight is going to be equal to the reaction force of the ground. Levers are simple machines that have an input and an output. The input force is usually referred to as the effort and the output as the load. Levers have a point of rotation that these forces will turn about. This point of rotation is known as the pivot or the fulcrum. The pivot or the fulcrum does not necessarily have to be in the middle of the lever. Only in first class levers they will be in the middle, as you can see in this pair of scissors. In second class levers, the force is in the middle, such as in this wheelbarrow, and third class levers, as you can see in the bicep, the effort is in the middle. The principle of moment states that the sum of clockwise and anti-clockwise moments about the same pivot is equal at equilibrium. Basically, both moments have to balance out in order for the seesaw to balance. On this particular diagram, we can see Odie the dog and Garfield the cat. Odie is sitting on the left, and thus he is creating an anti-clockwise moment about the pivot here. Garfield is creating a clockwise moment here. For them to balance, both of these have to be equal. Now, a moment is the product of the force by the perpendicular distance from the fulcrum. So you always measure from the fulcrum. In the case here, let's start with Garfield's moment. His weight is 60 newtons and his distance is 2 meters. So 60 times 2 is 120. That is his moment in Newton meters. Odie's moment is going to be 50 newtons times d2. So the distance that he has to be, because he weighs less, he would have to be a little further from the fulcrum. So 120 is equal to 50 d2, thus d2 is equal to 120 over 50. He would have to be 2.4 meters away in order to balance Garfield. Garfield would be closer to the fulcrum because he is heavier. In the second example here, we can see the effort which is on the boy's arms. The load is his weight and the fulcrum is on his toes. He's doing push-ups. Now remember again, we always measure distances or perpendicular distances from the fulcrum. So we have to calculate what is the effort E. So we say F1D1 is equal to F2D2. F1, which is his effort on his arms, is unknown. And D1 is going to be distance from the effort to the fulcrum. And that will be 0.4 plus 0.8. And that will be 1.2. The moment created by his own body weight is going to be 600 newtons times the distance from the fulcrum, which is going to be 0.8. So that's going to be 600 times 0.8, and that's going to be 480. When we work it out, E is going to be equal to 400 newtons. Feel free to pause the video at any time to work out these problems. Here we have another example question. If C is the center of gravity of the plank, calculate the weight of the plank. The center of gravity, remember, will be the weight of the plank. The weight of the plank is actually able to balance this 300 Newton, the moments of this 300 Newton block and this 500 Newton block. Now, because there are basically three forces here, the weight of the 500 Newton block, the weight of the 300, and the weight of the plank, we are going to have to write the formula like this. F1D1 plus F2D2 is equal to F3D3. F1D1 is going to be 500 times the distance from the fulcrum, which is going to be 2, the sum of 1.5 and 0.5. So 500 times 2. F2D2 is going to be 300 times the distance from the fulcrum, which is going to be 0.5. 300 by 0.5. F3D3 is going to be the weight of the plank, which is unknown, that's by the center of gravity, times the distance from the fulcrum, which is 0.75. 500 by 2 is 1000, 300 by 0.5 is 150, is equal to 0.75 F3. 1000 plus 150 is 1150, is equal to 0.75 F3. F3 is thus 1150 divided by 0.75, and your answer will be 1533.33 newtons. That will be the weight of the plank. Hooke's law states that the extension of a spring is directly proportional to the force acting on it, given that it is within its elastic limit. The formula for Hooke's law is given as F is equal to Kx or F is equal to Ke, where F is the force, X is the extension, and K is the spring constant. In this diagram here, we can see that when a force F is applied, we get an extension X. If that force is double, we'll get double the extension, thus being directly proportional. The elastic limit of a spring is within the limit of proportionality between the force and extension. That means if too much force is applied, the spring can experience permanent deformation and thus would not be able to return to its original shape. Here we have a worked example of Hooke's law. A 200 Newton load is attached to a spring with an initial length of 100 centimeters. If its spring constant K is 5 newtons per centimeter, calculate the final length of the spring. Well, first we're going to put Hooke's law here. F is equal to Kx. So X is going to be equal to F divided by K. F, the force, is 200 and K is 5. So 200 divided by 5 is 40 centimeters. So thus the final length of the spring is going to be 40 centimeters plus the original length 100, which will give you 140 centimeters. Density is defined as mass per unit volume. The SI unit for density is kilogram per meter cubed. Here we can see the formula. Density is represented as the Greek letter rho. Floating occurs if an object's buoyant force is greater than its weight or if it is less dense than a medium. A greater surface area means it's more likely to float. That is why a heavy boat is able to float, because it has more contact with water and thus more buoyant force. Sinking is the opposite. It means an object's weight is greater than its buoyant force, or if it is denser than its medium. Relative density is a given ratio of the density of a substance in reference to the density of the medium. Basically, it tells how much more dense or less dense an object is compared to another, compared to its medium. So example, calculate the relative density of oil in seawater if oil has a density of 800 kg per meter cube and seawater has a density of 1020 kg per meter cube. The relative density will be the density of oil, that is the substance, divided by the density of seawater, that is the medium. 800 divided by 1020 will be 0.78. There's no unit with this. Basically, this means that oil is only 0.78 times as dense as seawater. It means it's less dense, and thus the oil will float in the seawater. Archimedes' principle states that the upward buoyant force that is exerted on an object immersed in a fluid is equal to the weight of the fluid displaced. Here we can see a 6 kilogram weight being totally immersed in water with a 2 kilogram buoyant force. That will give a net force of 4 kilograms, which will be the difference between 6 and 2. It means that this buoyant force here is going to displace 2 kilograms of water using this displacement can, as you can see here. Distance is how much ground an object has covered despite its direction. It is a scalar. Displacement is the overall change in position of an object in a straight line between its origin and destination. It is a vector. In this particular picture here, you can see a car going in multiple directions, and this will be the total distance covered, represented by the red line. However, if you was to take the shortest distance in a straight line between the origin or the start and the destination or the end, that would be the displacement. And the displacement would be a vector because there's only one particular direction involved. In a displacement time graph, the gradient represents velocity. In this particular one here, the line that is going up means that the object is moving forward. If we was to find the gradient, in this case here, we was to say 25 meters over 5 seconds, that will be 25 over 5, which is 5 meters per second, which will be the velocity of the object as it is moving forward. A straight line indicates that the displacement has not changed, which means that the object has stopped. A downward line means that the object is returning to its original position or it is reversing. Speed is distance per unit time. Speed is a scalar. Velocity is displacement per unit time. Velocity is a vector. The formula for each one: speed is distance divided by time, velocity displacement divided by time. The unit for each one is meters per second. If we had to convert kilometers per hour to meters per second, this is what we do here. We say we convert the 108 kilometers to meters, 108 times 1,000, and convert the hours to seconds. There are 3,600 seconds in an hour, 60 times 60. Divide these two and you'll get 30 meters per second. If you had to do it the reverse, instead of multiplying, we divide. So to convert 18 meters per second to kilometers per hour, 18 divided by 1,000 meters over 3,600 seconds, or 1 kilometer per hour. Remember, when you divide a fraction like this, you invert it. So this will be 18 times 3,600 over 1,000. When you work this out, you'll get 64.8 kilometers per hour. Acceleration is a change in velocity over time. The unit is meters per second squared. The formula is given as A is equal to V minus U over T, where V is the final velocity, U is the initial velocity, and T is time. Here we have an example question. Calculate a car's acceleration after braking for 4 seconds if the velocity decreased from 24 meters per second to 16 meters per second. The final velocity is going to be 16, the initial velocity is going to be 24, and the time is going to be 4 seconds. 16 minus 24 is negative 8 divided by 4, and the acceleration is going to be negative 2 meters per second squared. Basically, this means that the car is decelerating. It is losing minus 2 meters per second every second that passes. In this velocity time graph, the gradient represents acceleration. Upward line means uniform acceleration. Plateau means constant velocity, no acceleration or deceleration, and downward line means uniform deceleration. Also in the velocity time graph, the displacement traveled is represented as the area under the graph. The unit is meters. In this particular graph here, we can see that this forms a trapezium, and there are 3 sides we have to take note of. The top of it is called A, the bottom of it is called B, and there's the height of the trapezium. So if we find the area of the shape of the trapezium, we will actually get the total displacement traveled by this object here. A is going to be 1, B is going to be 5 units, and H is going to be 30 units. The formula for the area of a trapezium is a half A plus B times height. That will be a half 1 plus 5 times 30, and this will be 90 meters. If we can also find the area of this rectangle here and this triangle and find the sum and get the same answer. Newton's first law states that an object at rest remains at rest, or an object in motion remains in motion at a constant velocity unless an unbalanced force acts upon it. This basically means if there are no outside forces, a stationary object will not move unless pushed or pulled. If it means that an object is moving and there are no outside forces, the object will continue to move. It will not stop unless it was to come into contact with another force. Newton's second law states the force on a body is directly proportional to its acceleration, or F is equal to ma. Force is equal to mass times acceleration. In the diagram here, it basically shows that the more mass is the more inertia, and thus requires more force in order to get that object to accelerate. Less mass means less inertia, so there's less force needed to get it to accelerate. Here we have an example question. A 2,000 kilogram minibus increases its velocity from 8 meters per second to 14 meters per second in half of a minute. Calculate the force required to do this. First, we have to calculate the acceleration of the minibus. And this will be A is equal to V minus U over T. The final velocity is 14. The initial velocity is 8. And that divided by the time, which is half of a minute, is 30 seconds. So the acceleration is going to be 6 divided by 30, which is 0.2 meters per second squared. The force now would be F is equal to ma. The mass of the minibus is 2,000 kilograms, multiplied by 0.2 is 400 newtons. Newton's third law says that every action force has an equal and opposite reaction force, or it says if body A acts on body B, B would exert an equal and opposite force on A. In this example here with the missile, we can see that the action force is going to be the thrust, well, from the thrusters here, and the reaction force is going to be the missile moving forward. Another example would be a person swimming. You push the water backward, that is the action. The reaction would be the water pushing you forward. Linear momentum P is the product of a mass and velocity for an object traveling in a straight line. The impulse is the force that produces a change in momentum. On the diagram to the right here, we can see the two pool balls are of the same mass, and the white ball imparts all of its momentum onto the red ball, causing it to move at the same velocity as before. Momentum is equal to mass by velocity. The formula is P is equal to mv. Delta P is equal to force by time if you are to determine impulse. The unit for momentum is kilogram meter per second or Newton second, basically mass times velocity. The law of conservation of linear momentum states that with no external forces, the total momentum before collision is equal to the total momentum after collision. Here we have an example question. If the wreckage moves as a combined mass after collision, calculate its net velocity and direction. Here we have a car going east 24 meters per second and it's 1,200 kilograms. Here we have a truck going west at 5 meters per second and the mass is 4,000 kilograms. First, we have to find the momentum of the car and the momentum of the truck. The momentum of the car is going to be 1,200 times 24, and that's going to be 28,800. The momentum of the truck is going to be 4,000 times -5. Why negative? Because it's actually headed in the opposite direction. So the momentum of the truck is going to be -20,000. Now, the wreckage combined is going to be 1,200 plus 4,000. That'll be the mass, 5,200. The total momentum of the car and the truck before collision is going to be equal to the total momentum after collision. So the total momentum is going to be 8,800 and that's going to be equal to 5,200 V. The velocity that the wreckage is going to move is thus going to be 8,800 divided by 5,200 and that will be 1.69 meters per second. It will be east because the car had more momentum than the truck. Because the car had a momentum of 28,800, the truck had -20,000. So we'll go in the direction of the car. Energy is simply defined as a capacity for doing work. The SI unit for energy is given as a joule. A joule is defined as the work needed to move 1 Newton by a 1 meter distance. So 1 joule is equal to 1 Newton meter. The law of conservation of energy states that energy can neither be created nor destroyed. It can only be converted from one form to another. Here we have several forms of energy: chemical, kinetic, gravitational potential, elastic potential, thermal, electromagnetic, and nuclear. So for example here, chemical energy in batteries are converted to electrical energy. Or when an object is falling, If you have a boulder on a cliff, it will have gravitational potential energy, but when it is falling, that would be converted to kinetic energy. Work or work done is energy used to produce some type of mechanical change. For example, if you used to lift a box and carry it up some stairs, this is also measured in joules. Power is the rate of energy conversion, and this is measured in watts or joules per second. The formula for work is W is equal to F multiplied by D, and the formula for power is equal to E divided by T, or work done over time. Here we have an example question. A 500 Newton package is lifted 20 meters above the ground. This takes 25 seconds to occur. Calculate the work done and the power. Well, the work done would be the force times the distance. The force of the package or the weight is 500 newtons times the distance is 20. 500 times 20 is 10,000 joules. The power will be the work done over time. 10,000 joules over 25 seconds means that the power needed to do this would have been 400 watts or 400 joules per second. Efficiency refers to the percentage or ratio of useful output compared to total supplied input. This will be the formula for efficiency. Basically, what efficiency says is that it compares the total amount of energy put into a system to the amount of useful energy. So for example, also light bulbs are not very efficient because they produce heat instead of light. Kinetic energy is the energy possessed by an object in motion or during collision. The formula for kinetic energy is a half mv squared. Gravitational potential energy is the energy possessed by an object by virtue of its position or height. The formula for gravitational potential energy is delta GPE is equal to mg delta h, where m is the mass, g is acceleration due to gravity, and delta h is the change in the height. If we have an object that is falling, if it's just being held in place at a certain height, it would have gravitational potential energy. When it is falling, it would convert that into kinetic energy. Here we have an example question. A coconut of mass 2 kilograms falls from a distance of 30 meters to 10 meters. Assuming negligible air resistance, calculate the velocity as it falls, and g is 10 newtons per kilogram. First, we're going to work out how much gravitational potential energy the coconut had. So you're going to say mg delta h. The mass of the coconut was 2, g is 10, and the change in height would be the difference between 30 and 10. That would be 20. So 2 times 10 times 20 is going to be 400 joules. Now, because there's negligible air resistance, we're going to assume that 100% of the gravitational potential converted to kinetic. So the formula for kinetic energy is equal to a half mv squared. They are asking for the velocity as it falls, so we're going to rearrange this formula to find for v squared, or v. So v squared is going to be equal to the kinetic energy divided by half of m. 400, it was the kinetic energy we would have worked out before, because all of it would have converted from gravitational potential, divided by half of the mass. The coconut had a mass of 2 kilograms, and half of that is 1. So that would leave us still with 400. So if v squared is 400, v is going to be the square root of 400, so the velocity is going to be 20 meters per second. Here we have a pendulum, and we just have to note how kinetic energy and potential energy changes as a pendulum swings. At positions 1 and 5, we could see that they are at its highest. So this would have the maximum gravitational potential, but also the least kinetic energy. At position 2, gravitational potential is converted to kinetic. At position 3, it is at the lowest height, so this would have the least gravitational potential. And the highest kinetic is basically swinging its fastest at 3. At 4, that kinetic energy is converting back to gravitational potential as it's swinging up. You have to be aware of at least 3 or 4 different alternative energy sources. These replace fossil fuels and are typically renewable. Solar panels convert sunlight to electric. Hydroelectric dams convert the kinetic energy from water to electric energy. Geothermal uses kinetic energy from steam wells below the surface of the earth. Tidal uses the natural ebb of the ocean and waves. Biofuel uses methane or ethanol from harvest, for example from corn. Wind turbine uses the kinetic energy from natural winds, and nuclear uses uranium fission in nuclear reactors to yield high amounts of energy. Nuclear energy is non-renewable, but all the rest here are renewable resources. How do we reduce energy wastages? Well, you could switch from incandescent to fluorescent lights because they are more efficient. Carpooling and public transport cuts down on fuel use. Turning off lights or AC units when not in use. Use more energy efficient appliances. And there's been the advent of hybrid or electric vehicles that cut down on the usage of fossil fuels. Pressure is force acting per unit area. The formula is P is equal to F over A. Pressure is measured in pascals or Newton per meter squared. If there's a smaller surface area, it means that there will be more pressure. If there's a larger surface area, it means that there will be less pressure. Pressure in a fluid increases with depth and density of the fluid. If you are finding pressure in a fluid, the formula you're going to use is P is equal to rho GH, where rho is density, G is acceleration due to gravity, and H would be height or depth. In a fluid, the deeper you go will be more pressure because there will be more molecules above that certain point and thus more weight. Here we have an example question. Calculate the total pressure at the base of a 20 meter deep container of oil of density 800 kg per meter cube if the atmospheric pressure is given as 101 kilopascals. Well, the pressure is the density times G times H. The density is 800, G is 10, and 20 meters deep. 800 by 10 by 20 is 160,000 pascals. That will be the total pressure of the oil. But the total pressure overall is going to be the pressure of the oil plus the pressure of the atmosphere, because the atmosphere is pressing down as well. So that will be the pressure of the oil, 160,000 pascals plus 101,000 pascals, and that will give a total pressure of 261,000 pascals. A manometer is used to find pressures of fluids of interest. The difference in column height is used to calculate the pressure. In this particular example here, we use mercury to determine the pressure, so the unit is millimeters mercury. So the column now, you'll see 40 millimeters and 70 millimeters for the atmosphere. We can see that the unknown pressure is pushing more than the atmosphere because this column here is lower down. What is the total pressure of the gas P in millimeters mercury? First, we have to find the change in height. That will be 70 minus 40 in this case, which is 30 millimeters. Now, because the pressure of the unknown pressure P is greater than the atmosphere, we're going to add that to the atmosphere. So the pressure of P is going to be 760 plus the difference 30. That will give you 790 millimeters mercury. Pascal's law states that the pressure applied to a point in an incompressible fluid is evenly distributed to all points in that fluid. So when this piston is pressed down, that is going to exert a pressure on this point, but that pressure is going to be the same throughout the entire fluid once it is incompressible. Now, on the other end, you're going to see that this has a wider surface area to lift the car. A wider area means that a larger force is being applied. The pressure exerted by the fluid is equal at all points. So the pressure applied on the small piston on the left is going to be the same as the pressure on the right, but the force is going to be a lot more. We're going to apply some numbers to this example here. 40 newtons being applied on a 10 meter squared piston, and the ram is 50 meters squared. Now remember, the pressure will be the same on both sides, so F1 over A1 is equal to F2 over A2. F1 is 40, A1 is 10, F2 is unknown, A2 is 50, cross multiply, 10 F2 is equal to 40 times 50, and you're going to get F2 is equal to 2000 divided by 10, which will be 200 newtons. Easy way to do it. We see that 10 can go into 55 times, so that means the force is going to be 5 times greater here. 40 times 5 is 200 newtons. Heat is a form of energy that is transferred from areas of higher temperature to lower temperature until the objects and their surroundings are at equilibrium, the same temperature. Heat energy is converted from mechanical energy. The scientist James Joule proved this with the experiment set up below. Basically, he had some paddles that were constantly moving and shifted by this weight here, and when this water began to move, he noticed that the temperature began to rise, and thus mechanical or kinetic energy converted into heat energy. The kinetic theory of matter indicates that molecules in a gas move freely and rapidly along straight lines. In a liquid and solid, intermolecular bonds form, which reduce the movement in the medium. On the left here, we'll see that we have a solid, the bonds break, it turns into a liquid, bonds break even more, and then we have a gas. If we had to compare solids, liquids, and gases, we can see that in a solid, the bond strength is the highest, in a gas it is the lowest. Solid has the highest density, gas has the lowest density. Gas has the highest volume, solid has the lowest volume. Liquids and gases basically take the shape of their container, but solids don't. Molecules vibrate in place in a solid, it has a fixed shape. Liquids take the shape of a container, just like gases. Gases have the most kinetic energy, the molecules move in a random, haphazard motion. Temperature represents the average kinetic energy per molecule in a substance. Its SI unit is Kelvin. To convert to Kelvin, you have to add 273 to the Celsius value. So for example, 100 degrees Celsius in Kelvin would be 100 plus 273, which is 373 Kelvin. The lower fixed point is the temperature of pure melting ice at 1 atmosphere. Its value is 0 degrees Celsius or 273 Kelvin. The upper fixed point is the temperature of pure dry steam at 1 atmosphere. Its value is 100 degrees Celsius or 373 Kelvin. Absolute zero is the temperature at which there is no heat or internal energy in the molecules. Its value is given as minus 273 degrees Celsius or 0 Kelvin. At this point, the pressure is 0. So if you was to graph it and we had pressure and temperature here, in Celsius, the pressure is going to be 0 at minus 273.15, which is absolute zero. A thermometer has a physical property that changes steadily with temperature. Example, in a liquid and glass thermometer, when the mercury is heated, it expands proportionately and moves along the bore of the thermometer. The more it is heated, the more the mercury expands, and thus the reading on the thermometer would be higher and higher in terms of degrees Celsius. A clinical thermometer is different from a liquid in glass because it has a thinner, larger bulb, which allows faster or more rapid conduction, a narrower bore, which means it allows for more sensitive readings. You are able to tell more specific readings, and a constriction, which prevents the liquid from immediately returning to the bulb. Typically, the doctor would have to shake the thermometer for the alcohol and mercury to return to the bulb. Another thing to note here is that the range of the clinical thermometer is usually lower. It might be between 34 and 44 degrees Celsius. A thermocouple uses differences in voltage between hot and cold junctions for rapid, accurate temperature readings. Conduction is the transfer of heat through the vibrations of molecules to adjacent molecules in a medium. Convection is the transfer of heat through bulk movement of the medium itself. Usually convection currents are created due to differences in density. When something warms up, it gets less dense. When something cools down, it gets denser. Radiation is the transfer of heat through the propagation of electromagnetic waves. It can occur through a vacuum. This is how heat from the sun travels through the vacuum of space to reach Earth. Conductors are materials with free electrons, such as metals, which allow the efficient transfer of heat. Insulators do not have many free electrons and may have structural gaps and air spaces that do not efficiently transfer heat, such as cloth or polystyrene. These would have air spaces, and since air is a poor conductor of heat transfer would not be efficient. Vacuum flasks keep liquids at constant temperatures by limiting heat transfer. So vacuum flasks would have a cover, and this would prevent heat from escaping through the top via convection. It would have an evacuated space, basically an area with no air, between where the fluid is supposed to be and the casing, and this means that it would limit how much conduction, because conduction requires a medium. Then there will be shiny inner walls to prevent or limit how much radiated heat can enter or escape from the flask. This would reflect any radiated heat away. Good absorbers and good emitters of heat are usually black in color, rough in texture, small in area, dull in nature. Good reflectors of heat are usually the opposite, white in color, smooth in texture, large in area, shiny in nature. Specific heat capacity of a material is defined as the amount of heat energy required to change the temperature of 1 kilogram of a material by 1 Kelvin. This is the formula for specific heat capacity. It is a constant. EH, which means heat energy, is equal to mc delta T. M is mass, common C is specific heat capacity, and delta T is the change in temperature. So if you have water, water has a specific heat capacity of 4200 joules per kilogram Kelvin. If the temperature of 1 kilogram of water is to be raised by 1 degree, so for example from 10 degrees Celsius to 11, it would require 4200 joules to do so. If you was to raise it by 2 degrees, for example from 10 to 12 degrees Celsius, it would require double that energy, which would be 8400 joules. Materials with very high specific heat capacities require a lot of energy to change its temperature. So for example, metals have lower specific heat capacities. That is why they heat up so quickly. They only require a little bit of energy before the temperature rises. Here we have an example question. A 1.2 kilowatt heater was used to heat a 2 kilogram mass of water for 5 minutes. The initial temperature of the water is 20 degrees Celsius. If the specific heat capacity of water is 4200 joules per kilogram Kelvin, calculate the final temperature of the water. First, we need to calculate how much heat energy is going into this water. So we use the formula power is energy over time. Energy is thus power by time, 1200 watts. By 5 minutes, which will be 5 times 60 seconds. You multiply these two, we're going to get 360,000 joules. Use the formula for specific heat capacity. E is equal to mc delta T. Rearrange it. Delta T is thus equal to E divided by mc. The energy is 360,000 joules divided by the mass, which is 2, times the specific heat capacity, which is 4200. When you work this out, you'll get 42.86 degrees Celsius. This will be the change in temperature. So that means that the final temperature is going to be the initial temperature, which is 20, plus the change. And thus your answer is going to be 62.8 degrees Celsius. Heat capacity, on the other hand, of a body is defined as the amount of heat energy required to change the temperature of the body by 1 Kelvin. In this case here, we are talking about a body instead of a material, so it's not per kilogram. The formula is given as capital C is equal to M common C. Capital C is heat capacity and common C is specific heat capacity. So example of this would be water has a specific heat capacity of 4200 joules per kilogram Kelvin. But let's say that we have a large container of water of 10 kilograms. How much energy would be needed to change that by 1 degree? Well, it would need 10 times the amount. So it would require 42,000 joules mass times the specific heat capacity MC to change or raise the temperature of the 10 kilogram container of water by 1 Kelvin. Here we have another example question. The metal aluminum block is heated for 3 minutes with a 5 amp current 10 volt supply. If the initial and final temperatures of the 2 kilogram block are 30 degrees Celsius and 35 Celsius respectively, calculate the specific heat capacity. In this case here, we need to use the formula for energy involving electricity, which is current by voltage by time. The current is 5, the voltage is 10, and the time is 3 minutes, so 3 times 60. Multiply these, and you're going to get the energy is 9,000 joules. You use the formula E is equal to mc delta T. Rearrange it to find for C is equal to E divided by m delta T. So 9,000 divided by 2 kilograms, multiplied by the change in temperature, which is going to be 5. So 9,000 divided by 10 is going to be 900 joules per kilogram degrees Celsius. Method of mixtures is another example of how you can use to determine specific heat capacity. In this case here, you're going to work with the concept of the heat gained by the water is equal to the heat lost by the metal. So here we have a 50 gram metal block is placed in 200 grams of water. The block was heated to 100 degrees Celsius and the temperature of the block dropped to 30 degrees Celsius. So we had a 70 degree drop there. The water rose from 30 to 35, so we had a 5 degree raise there. Using 4.2 joules per gram Kelvin as the specific heat capacity of water, calculate for the block. So we're going to say that mc delta T for the water is going to be equal to mc delta T for the block. Everything here in blue is with the water, so the mass of the water is 200. The specific heat capacity of the water is 4.2, and the change in temperature for the water is going to be 5 to the 5 minus 30. For the block, everything in orange is going to be for the block. The mass of the block here is 50. C is the unknown, and the change in temperature for the block is going to be 70, which is the difference between 100 and 30. So 4200 is equal to 3500 C. So C is going to be equal to 4200 divided by 3500. So the specific heat capacity for the block is going to be 1.2 joules per gram Kelvin. Remember, feel free to pause the video and work these out for yourself. Specific latent heat of fusion is the energy required to change 1 kilogram of a solid to a liquid without a temperature change. Specific latent heat of vaporization, on the other hand, is the energy required to change 1 kilogram of a liquid to a gas without a temperature change. So fusion is solid to a liquid, vaporization is liquid to a gas, or vice versa. The unit for each is joules per kilogram. There is no degree Celsius or Kelvin here because there is no temperature change whenever latent heat is being absorbed or emitted. The formula for each one is going to be E is equal to ml, but you're going to put a little F for fusion and a V for vaporization. In this cooling curve here, when latent heat is being released or absorbed, there is no temperature change. So that would be between B and C and D and E. This is why the temperature remains the same at these points here. And in this case here, the state of matter is changing as molecular bonds are broken or reformed. In this case here, between B and C, the gas is turning into a liquid, and between D and E, the liquid is turning into a solid, or the liquid is freezing in this case here. Latent heat in both these cases are being lost. Here we have an example question. A student heats 200 grams of ice at 0 degrees Celsius until it turns to steam at 100 degrees Celsius. How much energy was needed to do this? Here we can see we have three constants: the specific heat capacity of water, the latent heat of fusion of ice, latent heat of vaporization of water. What we have to do is work out how much energy is needed to melt the ice and turn it into water without a temperature change, how much energy is needed to raise the temperature of the water from 0 to 100, and how much was needed to boil the water and turn it into steam without a temperature change. So everything here is color coded according to the constants. So for the first one, to melt the ice, we're going to use E is equal to mLF. The mass, we're going to convert 200 grams to 0.2 kilograms, so 0.2 times the constant given here is going to be 67,200 joules. Now to raise the temperature, we're going to use E is equal to mc delta T. 0.2 times 4200 times 100 minus 0, which is 100. And we use this constant here. This will be 84,000 joules. To boil the water, E is equal to mLV. 0.2 times this constant here, you'll get 450,000 joules. Finally, the total energy to do all this, you just have to add these three answers together, and your answer is going to be 601,200 joules. Air pressure is the result of the collisions of gas molecules with the walls of the container that the gas is held within. The higher the frequency of collisions with the walls, the higher the pressure. The number of gas molecules in the container will also increase the frequency of collisions and increase the pressure. Basically, you have more molecules in here, you're going to get them colliding with the walls more and more often, and that's going to increase the pressure. Gas molecules in high temperature have more kinetic energy, and thus they will move faster. They will have more momentum and collide more often with the walls. Temperature and pressure have a directly proportional relationship. There are three gas laws: Boyle's law, Charles' law, and the pressure law. And there's a combination of the three called the general or the combined gas law. Boyle's law states that for a fixed mass of gas at constant temperature, pressure, and volume are inversely proportional. The formula is given as P1V1 is equal to P2V2. Basically, this means with a low volume, there's going to be high pressure, and with a high volume, there's going to be low pressure. And this is what the graphs would look like here. Now, the reason why a low volume is going to be high pressure is because at low volumes, there's going to be less space for the molecules to move, and thus they'll collide more often. With high volumes, they're going to have more space to move and they're going to collide less often. Here we have an example. A syringe at a fixed temperature has a gas at an initial volume of 50 milliliters at 4 kilopascals. At what volume would the pressure be 10 kilopascals? Use the formula P1V1 equals to P2V2. 50 is P1, V1 is 4. P2 is 10, V2 is unknown. When you work it out here, 50 times 4 is 200 is equal to 10 V2. V2 would be 200 over 10, which is 20 milliliters. Charles' law states that for a fixed mass of gas at constant pressure, Volume and temperature are directly proportional. The formula is given as V1 over T1 is equal to V2 over T2. Basically, this means that if you have a high temperature, that gas is going to occupy a high volume. A low temperature is going to occupy a low volume. So this will be the two graphs here. Note that the top graph, the temperature is in Kelvin. So when the temperature is 0, which means absolute 0 in this case, the volume is going to be 0 near 0. And in this one here, where the temperature is in Celsius, the volume is going to be 0 at minus 273, which is the same as 0 Kelvin. Here we have an example using Charles' law. When filled with 24 meters cube of helium at a temperature of 32 degrees Celsius, a hot air balloon is able to float. What is the volume of the balloon at 75 degrees Celsius? This is the formula here. Now, what we have to note is that we have to convert any temperatures, any Celsius temperatures to Kelvin. So the initial temperature is 32 and the final temperature is 75. We add 273 to them here and we get 305 K as T1 and 348 K as T2, K meaning Kelvin. 24 over 305 is equal to V2 over 348. We're going to cross multiply and I'm going to say 305 V2 is equal to 24 times 348. Feel free to work it out yourself. In the end, you're going to get V2 is equal to 27.38 meters cubed. It makes sense. If the temperature is higher, it's going to occupy, the gas is going to occupy more volume. Finally, here we have the pressure law, which says for a fixed mass of gas at constant volume, pressure and temperature are directly proportional. The formula is given as P1 over T1 is equal to P2 over T2. The graphs look almost exactly the same as the Charles one. Instead of volume, we have pressure. And basically at high temperatures, we're going to have high pressure because those molecules are going to be moving much faster, hitting much harder, and thus the pressure is going to be more. At low temperatures, it's going to have low pressure because the frequency of collisions and the force of those collisions are going to be less. Here we have an example using the pressure law. A car tire is pumped to a pressure of 2 times 10 to the power 5 Newton per meter squared, that is pascals, when the temperature is 23 degrees Celsius. Later in the day, the temperature rises to 34 degrees Celsius. Calculate the new pressure in the tire if the volume was constant. This is the formula here. Once again, we convert the Celsius values to Kelvin as seen here. 23 plus 273 is 296 Kelvin. 34 plus 273 is 307 Kelvin. So 2 by 10 to the power 5 is 200,000 over 296 is equal to P2 over 307. Feel free to work it out yourself, but when you cross multiply, you're going to get 296 P2 is equal to 200,000 times 307. In the end, P2 is going to be 207,432, which you can put in standard form as 2.07 by 10 to the power 5 pascals. Once again, we have seen an increase in temperature, which would lead to an increase in pressure. Finally, here we have the combined gas law, but in this scenario, no factor except the mass of the gas will be constant. So the formula is basically going to be a combination of the three. P1 V1 over T1 is equal to P2 V2 over T2. Now, when doing a gas law question, it'll be wise to start with this formula instead of memorizing the previous three, because you can always just eliminate which of the quantities is constant. So for example, if temperature is constant, you just cross off the two T's here and you are left with P1 V1 is equal to P2 V2. If volume is constant, you cross off V1 and V2 and you get P1 over T1 is equal to P2 over T2. So memorize this one formula instead of the three before. Here we have an example question with the combined gas law. An ideal gas has a volume of 150 cm cube at a temperature of 300 Kelvin and a pressure equivalent to 76 centimeters mercury. What will its volume be if the temperature goes up to 320 Kelvin and the pressure drops to 70 centimeters mercury? We use the formula here, and pressure 1 is going to be 76, volume 1 is going to be 150, and temperature 1 is going to be 300 kilograms. This will be the initial. The final, P2 is going to be 70, V2 is unknown, and the final temperature is going to be 320. What we're going to do now is we're going to cross multiply. We're going to say 76 times 150 times 320, which we're seeing here, is equal to 300 times 70 times V2, which is what you're seeing here. When you work it out, in the end, you are going to get this answer here. V2 is going to be 173.71 centimeters cubed. Feel free to try it yourself. A wave is a disturbance or propagation of energy from one location to another. Now, waves can be single oscillations or wave pulses, which means that there are no repeated oscillations, or they can be progressive waves, which basically means that the wave is moving through a medium, transferring energy continuously as it travels. Some waves can also move through vacuums, such as light. The wavelength of a wave is the distance between any two successive points in phase. In phase means that they are on the same position of the oscillation. In this case here, if we take this point here, which is the top of the crest of the wave, and this point here, which is also the top of the crest of the wave, the distance between these 2 points will be called a wavelength. The amplitude is the height of the wave or the maximum displacement of the oscillation. In this case here, this will be the distance between the resting point 0 and the maximum displacement, which should be the top of the crest or the very bottom of a trough of a wave. The distance between those 2 points is called the amplitude. The period, or T, is the time taken for one complete oscillation. One complete oscillation means that this is the time taken for one crest and one trough of the wave. And from the graph here, we can see that this is 0.6 seconds will be the period of the wave. The frequency is the number of oscillations passing a point per second, basically how frequently the oscillations occur. So in this case here, we can calculate the frequency of the wave, and this will be 1 divided by the period. So this will be 1 divided by 0.6 seconds, which is equal to 1.67 hertz. This means that for every second that passes, there will be 1.67 waves, or 1 2/3 waves. And here we can kind of see it here. Here we have 1 second, and this will be 1 wave, and this will be 2/3 of a wave over here. Here we have an example of how to calculate period. The maximum of the audible range of a human is 20,000 hertz, which again means 20,000 waves per second. Calculate the period of the sound wave, which is the time taken for one particular wave. So the period is equal to 1 divided by the frequency. This will be 1 divided by 20,000 hertz, and your answer is going to be 0.00005 seconds will be the time for one oscillation. High frequency waves have more oscillations per second. Here we can see a high frequency wave, and we can see that the cycles occur a lot more often and the waves are closer together, so the wavelengths are shorter. High amplitude waves are taller and have greater displacement. So for example, we can see a low amplitude wave is very short, and a low frequency, which means that the waves are further apart, they don't occur as often. But if you look at a high amplitude, high frequency wave, we can see that the waves are taller and they occur more frequently or more often, so they have a higher frequency. The velocity of a wave is calculated using this formula: V is equal to F lambda. Lambda is a Greek symbol for wavelength, F is frequency, V is velocity. So if a sound wave has a frequency of 15 Hz and a wavelength of 22 meters, calculate its frequency. We just employ the formula: V is equal to F lambda, F is 15 Hz, the wavelength is 22 meters, multiply the two and we'll get 330 meters per second, which is the typical speed of sound in air. Transverse waves are waves with crests and troughs, and the displacement of particles is perpendicular to the propagation. Basically what this means, propagation means the direction in which the wave is moving, which you can see here is to the right. The displacement of particles is the direction in which the source is moving, which you can see right here is up and down. That would be at right angles to the direction the wave is moving. That is why it's considered perpendicular. Examples of such transverse waves are light, radio waves, gamma rays, and X-rays. Longitudinal waves are waves with compressions and rarefactions. Compressions are areas where the particles are closer together, rarefactions are where they are further apart. And the displacement of particles is parallel to the propagation. Here we can see in the slinky spring, we can see that there are no crests and troughs. We have an area where it's close together, which is this is a compression moving to the right. And the wave is propagating to the right, and also the energy source, which is the hand, is moving left and right to create this wave, which means it's parallel. An example of longitudinal wave is sound. Sound waves are longitudinal and mechanical in nature. Mechanical means that they require a medium to propagate. Sound cannot propagate through a vacuum such as space. The denser the medium, the higher the velocity, because there are more particles in a dense medium. This means that sound would travel fastest in a solid and slowest in a gas. Here we can see an example of how sound would propagate as a longitudinal wave through a medium. The more particles means that the faster that the energy can be transferred from one location to the other location. Pitch correlates to frequency, and loudness correlates with amplitude. Now here we can see what a high amplitude sound would look like. This would be a very loud sound. Pitch high pitch and low pitch. High pitch, high frequency, low pitch, low frequency. Now the human audible range is 20 Hz to 20 kilohertz or 20,000 Hz. Basically, humans can hear anything within that range. As they get older, that drops a little bit. But if there's something that is below that or above that, if there's a sound that is above that, that is called an ultrasound, which you might be familiar with in terms of detecting babies in the womb. An echo is a reflection of sound. They are usually using sonar to detect sea depths or sometimes oil spills. How this works is an ultrasound signal is sent by a transducer, which would then reflect off of a dense surface and is picked back up by a detector. The time would be recorded between where this wave would go down and come back up. Now remember that the wave is traveling a distance down and a distance back up, so that means it's traveling double the distance. This is why the formula for it is calculated as speed is equal to 2 distance over time. Here we have an example problem involving echoes. In an experiment, Ravi stands 60 meters away from a wall and claps 2 blocks together 20 times. Chantal records the time for the 20 echoes as 7.2 seconds. Calculate the speed of sound from this data. So first we have to find the time for one echo. So we're going to take 7.2 seconds and divide it by the number of echoes, which is 20, and that will be equal to 0.36 seconds as the time for one echo. The speed will be double distance divided by the time, which means that this will be 60 times 2 because it had to go to the wall and return, and divided by 0.36. When you do that, your answer is going to be 333.33 meters per second. The electromagnetic spectrum tells the frequency and wavelength of a set of transverse waves that all travel at the speed of light, or 3 times 10 to the power 8 meters per second. In order from the lowest frequency to the highest frequency, it is radio, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. You can easily just remember the acronym. Rich men in Vegas use expensive gadgets to remember the order, which will be radio, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. Memorize the order in terms of frequency, memorize the backwards order in terms of wavelength, and have at least one use for each one. Diffraction occurs when a wave passes through a narrow aperture or opening and thus spreads out over a large area as it continues to progress. Every wave can undergo diffraction, whether it be water, light, or sound. For example, if we look at the diagram here, if we look at it from a bird's eye view, here we can see the waves coming from the top, and this is imagine these are the crests of the waves, and this is the aperture that it is passing through, and here we can see the waves are kind of curving as they're exiting here. Note that the wavelength doesn't change. Interference occurs when 2 waves superpose with each other to form a resultant wave that might either raise or lower the amplitude. So for example, here if we look at these 2 waves, this is the resultant wave below. We can see that when they are in sync, kind of like this, or when they are in phase, the amplitude of the wave is very, very high, such as 3, 2, 1 right now. Now, this is called constructive interference. It means that the waves are exactly superposed. Destructive interference means that the waves are out of phase by half of a wavelength. Basically, when a crest of one of the waves lines up with the trough of the other, such as 3, 2, 1, go. And you'll see that there's no wave at the point where there's destructive interference. It comes as if the wave is cancelling each other out. There are 4 theories of light that occurred over the years. The first one is by Isaac Newton, who said that light is a stream of particles or corpuscles. The next one is by Christian Huygens, who said light is a transverse wave. Next one is by Thomas Young, who proved that light is a wave by using his double slit experiment, and he said that it can undergo interference. The final saying is by Albert Einstein, who said that light can behave as both a wave and a particle, and this is called the quantum theory. This is Young's double slit experiment. Basically what he did was set up a light bulb in front of 2 cards, one with a single slit and one with a double slit, 2 small holes there. The light was able to diffract through these small holes because of its small wavelength. Now what he observed on the screen behind these cards here is that there were bands of dark and bright. He did not expect to observe this, but basically he called the dark parts minimas and the bright part maximas, and he said that basically if light behaved as particles, it would not form a pattern like this because particles cannot undergo interference. He deduced that when the waves are in phase or constructive interference, the crests and troughs are aligned with each other and result in bright fringes. These are called maximas. But when the waves are out of phase with each other, destructive interference, they result in dark fringes called minimas. Basically, this is when the troughs of one wave cancel out the crest of another. Reflection of light occurs when an incident light ray bounces off a surface. Here we can see an incident ray hitting off a surface here and becoming a reflected ray. Now you'll notice a normal in the diagram. So a normal is an imaginary line that is perpendicular to a boundary or surface. Now the normal will always be 90 degrees to the surface. All angles are measured from the normal. In this case here we have I, which is the angle of incidence, and R, which is the angle of reflection. You'll notice that the angles are always measured from the normal to the ray themselves and not from the mirror. Reflected images are the same height as the object, the same distance from the mirror as the object. They are always flipped sideways or laterally inverted. So for example, this word ambulance here would be flipped sideways or laterally inverted, because typically when you are going to see the word ambulance is because you're going to be looking in your rear view mirror. You're going to see the word correct in its correct orientation, and you are going to move out of the way and respond quickly to the ambulance as a result. Lastly, reflected images are virtual, which means that they cannot be projected onto a screen. There are two laws of reflection. The first law is the incident ray, reflected ray, and normal all lie on the same plane or same two-dimensional plane. The second law says that the angle of incidence is always equal to the angle of reflection. So for example, if the angle of incidence is 45 degrees, the angle of reflection is also going to be 45 degrees. If the angle of incidence is 0 degrees, the angle of reflection is going to be 0 degrees. Here we have a wave undergoing refraction. Now if a wave moves into a denser medium, its wavelength would decrease, is what you are seeing here. We see the waves are getting closer together. Its speed would decrease. We can see the wave is moving a little more slowly here, but the number of waves per second is going to remain unchanged. So the frequency is going to remain unchanged. So this is called refraction, and basically what's going to happen here is the wave is being propagated from one medium to another, but the second medium is going to have a different density from the first medium, causing the wave to bend. So in refraction of light, if we observe it here, in the glass block, the emergent ray is parallel to the incident ray. If we follow the cursor here, we can see the incident ray, then the angle of incidence. What's going to happen here is the wave is going to bend towards the normal, and this is going to be our refracted ray here, and then it's going to bend away from the normal as it exits, and this is going to be our emergent ray here. Now if this glass block wasn't here, we wouldn't get the ray bending at all because it would just keep propagating through the air. Because the glass block is denser than the air, the wave would refract upon entering and exiting the glass block. If the glass block was not here, this gray line would indicate the original pathway of the ray. The lateral displacement is the perpendicular distance between the original pathway of the ray and where the emergent ray stands now. The denser the medium, the greater the lateral displacement, because the denser the medium is the greater refraction that is occurring. Dispersion of light occurs when light comprised of various wavelengths passes through a prism. The light splits into different colors. White light, for example, is made up of all the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. As the white light enters the prism, we can see that it is being refracted but being dispersed into the different colors. As the light ray exits the prism, it is being diffracted again. Because red has the longest wavelength, it is refracted the least, and because violet has the shortest wavelength, it is being refracted the most. This is called dispersion. The refractive index of a material is the ratio of the sines of the angles of incidence and refraction of a ray passing from one medium to another. Basically, what refractive index means is how optically dense an object is. It also refers to how much more slowly light is going to travel through that medium. So for example, glass has a refractive index of 1.5. That means that light is going to travel 1.5 times more slowly through glass. The formula for refractive index is given as n is equal to sine I over sine r, where n is refractive index, I is the angle of incidence, and r is the angle of refraction. We can also calculate refractive index as n is equal to c over v, where c is the speed of light in a vacuum and v is the speed of light in a medium. Here we have a worked example for refractive index. Calculate the refractive index from air to glass. Above here, we can see the angle of incidence in the air is 40 degrees, and as it bends towards the normal to the glass, the angle of refraction is 25 degrees. We're going to say n is equal to sine I over sine r. The angle of incidence is 40, so this will be sine 40 divided by sine 25, which is the angle of refraction. When we work this out in our calculator, we'll get 0.64 over 0.42, and the refractive index from air to glass is going to be 1.52. Remember what this means? It means that light is going to travel 1.52 times more slowly in glass. Make sure that the calculator is set on degrees when you are doing these problems. Here we have another worked example for refractive index. Calculate the angle of refraction if n is equal to 1.5. Here we can see a light ray moving from medium A to medium B. The angle of incidence is 60 degrees, and we don't know the angle of refraction, but we know the refractive index is 1.5. We're going to write the formula here. N is equal to sine I over sine r. Rearrange it to say sine r is equal to sine I over n. This would be sine 60 over 1.5. Sine 60 is 0.87 divided by 1.5. You're going to get 0.58. What we're going to have to do with this number now is do sine inverse 0.58, and your angle R here will be 35.45 degrees. It makes sense because the angle here looks smaller and it would have bent towards the normal here. There are two laws of refraction. The first law is the incident ray, refracted ray, and normal all lie on the same plane. The second law is the refractive index is the ratio of the sines of the angles of incidence and refraction for a wave moving from one medium to the next. This is also called Snell's law. This is also just the definition for refractive index. So you can also just write the formula for refractive index. N is equal to sine I over sine r, and just indicate what is n, I, and r. The critical angle is the angle of incidence that produces an angle of refraction equal to 90 degrees. Here we can see the incident ray coming from glass to air. Now because air is less dense, we would expect this ray here to bend away from the normal. But what is happening here is the angle of incidence is so much that the ray cannot bend away from the normal anymore until it ends up at the boundary of the glass block here. This means that the angle of refraction is 90 degrees. When the angle of refraction is 90 degrees, this angle of incidence here that creates that is called a critical angle. In the case of glass here, the critical angle is 42 degrees. Now what if we had to calculate the refractive index if we know the critical angle? Well, we use this formula here. N is equal to sine 90 over sine C. Sine 90 in reference to the angle of refraction here. Sine 90 is equal to 1, so this will be 1 divided by sine 42 here. So 1 divided by 0.67, and your answer will be 1.49. Total internal reflection occurs if the angle of incidence surpasses the critical angle. The ray is reflected instead of refracted. So for example, what we can see here, this is your critical angle. So this is the angle of incidence, and this is the refracted ray here. Now if this critical angle was increased by even 1 degree, we are not going to see any refracted ray here. What we're going to see is just a reflected ray seen as below here. So this would be our incident ray and our reflected ray. Here we can see on the animation to the left, we can see it occurring here. Optical fibers, periscopes, and road reflectors all utilize the idea of total internal reflection. If you look at this sketch here of a road reflector, here we can see if we was looking at this incident ray, we can see that it enters the prism undeviated at an angle greater than the critical angle of glass, because this is actually going to reflect at 90 degrees. We're going to have an angle of reflection at 45 degrees, which is more than 42. It's going to reflect again undeviated, and thus is going to get totally internally reflected as it enters and exits the prism at 180 degrees. Convex lenses allow light rays to converge upon a singular point at the focal point. So here we can see the different parts of the ray diagram. We have the principal axis, which passes through the optical center of the converging lens or the convex lens. All these light rays that pass through the convex lens, you're going to see that they're going to converge upon one point. This point here is called F, or the focal point, or the principal focus. The distance between the focal point and the optical center of the lens is called the focal length. Examples of convex lenses include microscopes and magnifying glasses. Concave lenses, on the other hand, don't converge light, but they allow light rays to diverge or move outward like this. Examples would include flashlights and peepholes. Now, if we follow the ray here, we can see that this top ray, it diverges like this here, but if you have to draw the focal point, what you have to do is continue this ray as an imaginary line like this here until it touches the principal axis, and this will give you a focal point. Real images can be projected. They occur when the object distance is greater than the focal length. Virtual images cannot be projected. They occur when the object distance is less than the focal length. This is the formula for magnification. The magnification M is equal to the height of the image divided by the height of the object, or the distance of the image from the center of the lens to the distance of the object from the center of the lens. Magnification has no units. These are some examples of lens diagrams. Here we can see the object represented by the arrow, and this is the object between F and 2F. This will create an image I. We can see from this image that it is inverted, it is real, which means that it is projected on the other side of the lens, and it is magnified, meaning that it is bigger than the object. Here we have the object between F and the optical center, and this is our object here, which is the black arrow, and we can see that the object distance is less than the focal length, which will be the distance between F and the center of the lens. The image that we can see here that is formed is magnified, it is upright, and it is virtual, which means it's not projected on the other side of the lens. Here we can see a few more lens diagrams. Here we can see the object that is beyond 2F, and the image that is produced from it is diminished, which means it's smaller, it is inverted or upside down, and is real because it's projected on the other side. Now, if the object is placed on F itself, it means that the image will never form, but in physics and mathematics, they never say never, so you say instead the image forms at infinity. This is a concave lens diagram. You can take a look at it, but they don't really ask you about this at CXC. This is the lens formula, the lens equation. This is equal to 1 over F is equal to 1 over U plus 1 over V, where F is the focal length, U is the object distance, and V is the image distance, as you can see here. Remember, the focal length is the distance between the focal point and the optical center of the lens. The object distance is the distance between the object and the optical center of the lens. And the image distance is the distance between the image and the optical center of the lens. Here we have a worked example of a lens question. An object is placed 24 centimeters away from a convex lens of 8 centimeters focal length. Calculate the image distance V. So the object distance is 24 centimeters, the focal length is 8 centimeters. We're going to use the formula here. 1 over F is equal to 1 over U plus 1 over V. We're going to have to rearrange this to find for 1 over V. So 1 over V is equal to 1 over F minus 1 over U. So 1 over V is going to be 1 over 8 minus 1 over 24. We're going to find the LCM of this. 8 and 24, the LCM is 24. 8 can go into 24 3 times. 24 can go into 24 1 times. So you get 3 minus 1 is equal to 2 over 24. But this is 1 over V, so V is going to be the inverse of that. So V is going to be 24 over 2, which is going to be equal to 12 centimeters. Feel free to pause the video and try this for yourself. An example of electrostatics is when a silk cloth is rubbed with a glass rod, and here we can see the glass rod becomes positive and the silk cloth becomes negative. This is because the glass rod loses electrons and the silk cloth gains electrons. So the rod loses electrons and becomes positive, the cloth gains electrons and becomes negative. Now only negative charges move because those are electrons which are very light and are not bound to the nucleus. Positive charges don't move because they are bound to the nucleus of the atom, such as protons. Induction means objects can be placed next to each other using a charged object within proximity. This method is called charging by induction. So from the example that we can see here, from the animation, here we can see two neutral spheres. And when a negative object is brought to it, positive charges are attracted to it and negative charges are repelled to it, because like charges repel and opposite charges attract. When the spheres are separated, we can see that they now become charged. One of the spheres becomes positively charged, the other sphere becomes negatively charged. Charges are comprised of coulombs. Think of a coulomb as a bundle of electrons that can either be stored or transmitted. The formula for charge is equal to Q is equal to IT, where Q is charge, I is current, and T is time. A worked example is shown here. The makers of a cell phone have upgraded its battery capacity from 4,320 coulombs to 9,000 coulombs. If a charger delivers a current of 0.6 amperes, how much more time will it take to charge the new battery than the old? First of all, we can find the difference between the both batteries. So delta Q is equal to 9,000 minus 4,320, which is equal to 4,680 coulombs. Now the change in time will be that charge divided by the current when we transpose. So this will be 4,680 divided by the current 0.6. Our answer is going to be 7,800 seconds or 130 minutes. An electric field is defined as the region around a charged particle or object within which a force would be exerted or other particles or objects. From the diagram that you can see here, positive electric fields flow outward and negative ones flow inward. Now note that electric fields always flow from positive to negative. Here we can see a few circuit components. There are many more, but these are the ones that you have to know. Here we have a dry cell, a switch, a fixed resistor, a rheostat, a bulb or a lamp, a voltmeter, an ammeter, a fuse, a semiconductor diode, an AC power source, and a motor. Voltage is defined as the amount of energy contained per unit of charge. So therefore 1 volt is equal to 1 joule per coulomb. Voltage is also called potential difference or EMF, which stands for electromotive force. Think of voltage as the force that pushes charges across a conductor, as you can see here. Current is the number of unit charges that pass a point per second. So 1 ampere is equal to 1 coulomb per second. So for example, if you have a 2 amp charger for your phone, that means it will deliver 2 coulombs per second to the battery. If you have a 1 amp charger, it's only going to deliver 1 coulomb per second, so it'll take longer to charge your phone. Current flows conventionally from positive to negative. The opposite of that is called electron flow, which flows from negative to positive. Resistance is defined as the opposition to current flow in a circuit. So 1 ohm is equal to 1 volt per ampere. So here we can see an idea of resistance, where you would have a high flow of charges. Where you have resistance, you would have a lower flow of charges. So wires of thin diameter tend to restrict flow of current and so have greater resistance. Longer wires also have greater resistance due to heat losses. An easy way is to think of it as a pipe with water running through it. If the pipe is very, very thin, less water will be able to run through it. Ohm's law states that the current through a conductor is directly proportional to voltage and inversely proportional to resistance. There are two formulas involved in this. Ohm's law, the formula is given as V is equal to IR. Joule's law, the formula is given as P is equal to VI, where P is power, or I squared R. From the diagram here, you can see that, remember, voltage is the push, amperes is the rate at which those charges flow, and resistance measured in ohms restricts the flow of those charges or current. Here we have a worked example involving Ohm's law. A lamp is marked 12 volts, 3 amperes. Calculate the lamp's resistance and the energy if left on for a minute. So in the orange here, the resistance V is equal to IR. So therefore R is equal to V over I. This will be 12 volts divided by 3 amps, and your resistance is going to be 4 ohms. In the blue, we're going to calculate energy. So first we're going to calculate the power. P is equal to VI. This will be 12 volts times 3 amps, which will be 36 watts. So the energy will be equal to power by time, which will be 36 watts times 60 seconds because it's 1 minute. And our answer is going to be 2,160 joules. Now you can actually combine these two formulas into one and just say energy is equal to voltage by current by time, which is basically power by time. You'll get the same thing. Ammeters and voltmeters. Ammeters measure current and they are usually connected in series to what they are measuring, so due to their low resistance. So in this case here we have a resistor and the ammeter is connected on the same wire as this. Voltmeters, however, are connected in parallel. They measure voltage, and this is because they have a high resistor, so you only want a few electrons to come down here. You don't want it to interrupt the flow of the circuit. So direct current is unidirectional, which means it travels with one direction and has a mostly fixed value. Examples of direct current would be AA batteries. From the graph that you're seeing here, this is a direct current. The voltage pretty much remains steady as time passes. Alternating current, however, is bidirectional, which means that it travels both ways and has values that fluctuate between positive and negative. Examples of AC would be transformers and power lines. Here we can see an alternate alternating current, which is basically a transverse wave. The direction of the current is always switched periodically, and the voltage is also switched, where it is going between or oscillating between positive and negative, positive and negative, positive and negative. So an alternating current can be converted to a direct current with the use of a semiconductor diode, which is what you're seeing down here, or a rectifier. This produces half waves in a voltage time graph. So this diagram on the right, this one here, this would typically be an alternating current, which you can see fluctuating between positive, negative, positive, negative. When it passes through a diode, however, what happens is that the troughs are removed from the graph, so all you're left with the positive. So this would be a half wave output for a direct current. It would no longer be an alternating current. By the way, if the diode here was flipped, no current would flow because diodes only allow unidirectional flow. Primary and secondary battery cells. So here we have a primary battery cell, and primary battery cells cannot be recharged. They have a lower terminal voltage, a higher internal resistance, and the charges only flow from positive to negative if you're doing conventional current. Secondary cells, for example, can be recharged, have a higher terminal voltage, a lower resistance, and both positive and negative charges can flow, cations and anions. Primary battery cells would be like AA batteries, those that you put in your remote control. Secondary cells would be like lithium-ion batteries in your laptop or your cell phone, or lead-acid batteries in cars. Here we have 4 voltage current graphs that you should know. I would suggest pausing the video and taking a look at them. In series circuits, there is only one current path. Here we can see a battery cell of value 6 volts. The charges are going to flow out of the positive and into the negative. It is going to flow through A and B, which are 2 light bulbs. A has a resistance of 5 ohms, B has a resistance of 3 ohms. If either one of these light bulbs were removed, there will be no current flow because the circuit would be broken. The voltage in the cell is shared between A and B, so the 6 volts is going to be divided up between A and B. Higher resistances require more voltage. Current is equal in all components in series, so the current through A is going to be same as the current in B and all throughout the wire. Now if you wanted to find the total resistance in this circuit, all you have to do is add the resistances. In this case here, 5 ohms plus 3 ohms is 8 ohms. But let's look at the worked example here. Calculate the following: the total resistance, the current, and the voltage only through A. So the total resistance will just be R1 plus R2, which is 5 plus 3, which is 8 ohms. To calculate the current, I is equal to V over R. The voltage is 6 volts and the total resistance is 8 ohms. So 6 over 8 is 0.75 amperes. So this means that lamp A is going to have that current 0.75 amperes. Lamp B is also going to have 0.75 amperes. And so the battery is also going to have 0.75 amperes because the current is the same going into and out of each component. So the voltage through A, that will be equal to V is equal to IR. And remember, the current is going to be the same through A, B, and the battery. So you're going to use the same value here, 0.75 by 5. And this will be 3.75 volts. If you want to do for B, there will be 0.75 times 3. And that will be 2.25. And if you actually add the voltages of A and B, you will get 6 volts. In parallel circuits, there are multiple parts. Here we have the same components as the previous series circuit, but each bulb is wired individually, where A is 5 ohms and B is 3 ohms. So it means that if A is removed, current can still flow to B. If B is removed, current can still flow to A. The voltage in each part is the same as the voltage of the cell. So 6 volts is the battery. So this part 1 is going to have 6 volts and this part 2 is also going to have 6 volts. The current in each part is determined by the part's resistance. Higher resistances have lower current. So for example here, 5 ohms, which is the higher resistance, would have less current passing through here than part B. Resistance in a parallel circuit is calculated with the following formula. 1 divided by R is equal to 1 over R1 plus 1 over R2 and so on if there are more. In this case here we only have two resistors, so there's going to be 1 over 5 plus 1 over 3. The LCM of 5 and 3 is 15, so 5 into 15 is 3, 3 into 15 is 5, 3 plus 5 is 8 over 15, that's 1 over R, so that means R is going to be the inverse, so R is going to be 15 over 8, which is 1.875 ohms. Now what if you have to find current in a parallel circuit? Well, the total current can be calculated by finding the currents through each path. So path A, we can say I is equal to V over R. Now remember, each path has the same voltage as the source. So the voltage here is going to be 6. So there's going to be 6 volts divided by 5 ohms, and that's going to be 1.2 amperes. Part B, I is V over R, but down here we're going to say 6 volts over 3 ohms is going to be 2 amperes. All you have to do now is add it. 1.2 plus 2 is 3.2. But since we already had the total resistance of the circuit, we can also use this part here. I is V over R, where we use the total voltage divided by the total resistance. So the total voltage is 6, the total resistance was 1.875. Divide that, we're going to get the same exact answer as before. So we can use the total resistance, or we can just find the current through each part. This is a combined series and parallel circuit where we have sections that are in series but they are parallel to another section. So for example, in part B, R2 and R3 are in series with each other, denoted by the blue line. This is part B. And part A, which is the red line, we only have R1. So R1 is actually parallel to R2 and R3. Ammeter 1, what we are seeing here is measuring the total current in the circuit as it is connected to the power source, whereas ammeter 2, what you're seeing here, is only measuring the part of the current in A. Now what if we had to calculate the readings on both ammeters? How are we doing that? Well, let's start with ammeter 2, because this is only part A, which is the red line. So what we have to do is say I is equal to V over R. Then the voltage, the 12 volts, remember each pathway is going to have 12 volts. So part A is going to have 12 volts as well. Part B is also going to have 12. So all we have to do here is say I is V over R. Voltage is 12 divided by 2 ohms, which is the resistance of pathway A. So 12 over 2 is 6 amperes here. Now we can also find the current in part B by just adding the resistances here. Because they are in series, we're going to say 2 plus 4 is equal to 6 ohms. This is the total resistance of part B. Now in order to find the current here, we're going to say I is equal to V over R, and this will have a voltage of 12, and that will be 12 divided by 6, which is 2 amperes. So now that we've worked out the current in both part A and B, 6 amperes and 2 amperes, all we have to do to find the total is just to add them. So 6 amps plus 2 amps is going to be equal to 8 amps. Fuses are made up of metals with low melting points. So the fuse gets heated up, the fuse breaks, and the circuit is broken. Fuses and switches are always connected to live wires. Neutral wires complete the circuit, but they have a very, very low voltage, sometimes 0 voltage. And ground or earth wires deposit extra electrons into the ground. Live wires are usually brown or red, neutral wires are usually blue or gray, and earth wires usually are striped green and yellow. This here is the symbol for a fuse. Electrical hazards. So you have damp wires and broken insulation can result in electrocution or electrical fires. Electrocution can also occur if the earth wire or the grounding is improperly connected. This would cause electrons to build up in the frame of our appliance. So for example, when you touch a refrigerator and you get shocked. Temporary magnets, for example iron, can be easily magnetized and can be used in electromagnets. These are magnets that can be switched on and switched off. Permanent magnets, for example steel, retain their magnetism for a longer time and are usually found in compass needles and metal detectors. Also those little fridge magnets I have. An unmagnetized magnetic material can be magnetized if it is placed in the proximity of a magnet or an electric field. Now, magnetic fields run perpendicular to electric fields and are part of the same force. One cannot exist without the other. This is why it's called the electromagnetic force. So in this particular example here, we have the battery, and the battery is providing current, and the current is flowing into the conducting iron nail. Remember, iron is a temporary magnet. So when the circuit is connected, the electrons will flow from the battery to the iron nail, which will temporarily magnetize it. This hand here depicts Fleming's left-hand rule. Take careful note of how to do your fingers. Now the thumb represents the thrust. The first finger or the index finger represents the field, and the second finger or the middle finger represents the current. Two of the quantities can create the third once they are perpendicular to each other. What this means is that if you have any two of these three, the third one can be manifested. So for example, if a wire is moved or thrusted perpendicular to a magnetic field, a current can be induced in that wire. If a current carrying wire is perpendicular to a magnetic field, the wire will be thrusted in a certain direction. So once you have any two of these, the third one can be made. So remember how to do your hand. What direction is the wire being thrusted? Here we have an X, and that means that the current is going into the page. This is a wire and it's between a magnet here. Now the field always runs from north to south. So this means that your index finger is going to be up and your middle finger is going to be into the page because the current is going to go into the page. If you did it correctly, we're going to see how your thumb is going to be pointing. Your thumb is going to be the thrust. If you did it right, your thumb should have been pointing to the right. If that didn't happen, feel free to rewind the video and try it again. Here we have a second example. If the wire is being thrusted out of the page, is the current moving to the left or to the right? Now because the fields move from north to south, your index finger will be pointing up, north to south, and your thumb will be pointing out of the page because the wire is being thrusted out of the page. And you're going to see where your second finger or your middle finger is pointing. If you did it right, your middle finger should have been pointing to the right, which means that the current would be moving to the right on the wire. This is the right hand grip rule. Basically, you take your right hand and you make a fist with it with your thumb pointing out, which you can see here. Your thumb is going to indicate the direction of the current and your other four fingers are going to indicate the magnetic field. Here we can see two examples here. The X, which is this first diagram, means that the current is going into the page. So what you have to do is point your thumb into the screen, towards the screen, and look at where your four fingers are curling, and it's going to see that it's going to indicate a clockwise direction. When you see a circle with a dot on the other hand, it means that current is coming out of the page. What you're going to do is again make a grip, and you're going to have your thumb coming out of the screen and towards you, and you're going to look at your four other fingers and you're going to see that they're going to go in an anti-clockwise direction. Here we can see two worked problems involving the right hand grip rule, and in the first one here we can see there's a wire with the current flowing directly into the paper. It's going north to south. This is the magnetic field line, and we're going to see that on top here we're going to have a very strong magnetic field because they have a lot of them going in the same direction, and thus that is going to thrust the wire downwards. Here's the resultant of this here. This is going to be the opposite, but feel free to pause the video and take a careful look at the diagrams. In a coil, for example, here we can see that the current is flowing from positive to negative. So that means it's flowing from A to B, B to C, C to D, and back down here, positive to negative. So if you do your Fleming's right hand rule here, what you are going to get is a downward thrust at AB and an upward thrust on CD. Remember, the magnetic field travels from north to south. The current is flowing up at AB and down at CD. If you did it correctly, you're going to get this here. This is going to produce an anti-clockwise moment. Now, no thrust is going to occur on BC because the magnetic field will be parallel to BC, to the current at BC, not perpendicular. DC motors convert electrical energy to mechanical energy. Basically, it takes current to make something spin. So the motor spins due to forces created by the current being perpendicular to the magnetic field. In DC motors, we have a split ring or commutator, and what this does is that it breaks the circuit every half turn. This prevents the coil from reversing the direction and allows it to spin continuously. What if you had to generate more turning force on a motor? What can you do? Well, one, you can add more turns to the coil. You can increase the current of the power source, or the battery in this case, or you can use stronger magnets, and that would allow the loop to turn faster. AC generators converts mechanical energy to electrical energy. Basically, you spin something to create a current or voltage. An outside energy source, for example wind in a wind turbine, spins the external rotator, which turns the wire loop in the magnetic field. This would generate a current. So here we have the external rotator, and this is going to spin this loop here. You're going to have slip rings, not split rings this time, but slip rings, so that when the wires spin, there will be a constant point of contact, and this will generate a voltage that would light the bulb. If you had to generate more current or voltage, you can simply add more turns in the coil. You can rotate the coil faster or have more kinetic energy, or use stronger magnets. Electromagnetic induction, from what you are seeing here, basically if you are thrusting a magnet into a solenoid, you are going to induce a voltage or current in that solenoid or that coil. So the voltage induced in a coil is proportional to the rate of magnetic force across it, and this is Faraday's law as you see here. Now you're going to see as the magnet is going in and out, it is actually generating an alternating current. As you can see, the voltmeter is going side to side like this. No current or voltage is induced if the magnet is not moving relative to the coil. The galvanometer needle or galvanometer measures the direction of current, points up at 0. So if you just have the magnet resting inside of the coil, there will be no current induced, and thus there will be no flow of electrons. Transformers can either increase or decrease voltage. They do this by decreasing or increasing current, so it kind of trades one for the next one. Step-up transformers increase voltage by having more secondary turns than primary turns. So from here we can see that the primary voltage is 12 volts, but the secondary voltage is 220 volts, which means that it has been increased. This is because the number of primary turns is less than the number of secondary turns. Step-down transformers, on the other hand, decrease voltage by having less secondary turns. So here we can see the step-down transformer that is dropping from 220 volts to 12 volts because there are more primary turns than secondary turns. Transformers need an alternating current power source to allow for a constantly changing magnetic field in the primary turns. So basically what's going to have here is electrons are going to flow back and forth in this primary side of the transformer, and this is going to electromagnetize the core, and it's going to induce a current in the secondary turns. So the alternating EMF from the primary coil will electromagnetize the soft iron core because soft iron is a temporary magnet. Because the secondary coil in this turn has more turns, it will produce a higher voltage but with less current. This means it will step it up from 200 volts to 1000 volts. Now because 200 can go into 1000 5 times, this means that this will have 5 times more turns on the secondary coil than the primary. Here we have the two transformers formulas, which is NP over VP is equal to NS over VS, and IPVP is equal to ISVS. Of course, I means current and V means voltage, N means number of turns, P means primary, and S means secondary. Basically what this means is that NP means number of primary turns, NS means number of secondary turns, VP means primary voltage, VS means secondary voltage. The question here is to calculate the number of secondary coils and or turns on the secondary coil and the secondary current. So we're going to use the first formula here, NP over VP is equal to NS over VS. When we cross multiply this, we are going to get VSNP is equal to VPNS. So the secondary voltage is going to be 1000 volts multiplied by the number of primary turns, which is 5. So 1000 times 5. VP is going to be 200 is what you're seeing here, times NS is what you want to find. So 5000 is equal to 200 NS. So NS is 5000 over 200, and that will give you 25 turns. To calculate the secondary current, we just have to say IPVP is equal to ISVS, where the primary current is 15 amps as you are seeing here. The primary voltage is 200 is equal to the secondary current times 1000, which is the secondary voltage. 15 by 200 is 3000 is equal to 1000 IS, so IS is equal to 3000 over 1000, so our secondary current is equal to 3 amperes. Feel free to pause the video and go through this by yourself. Here we have another worked example. Electrical power produced by PowerGen in Trinidad is stepped up from 11,000 volts at 8,000 amps to 110,000 volts for transmission to Tobago. 1. If the number of turns in the secondary coil is 900, calculate the number of turns in the primary coil for an ideal transformer. Ideal transformer means that there's 100% transmission, there's no power losses. Calculate the transmission current for the ideal transformer in A. Take a look at the working on the right. Feel free to pause the video and go through it yourself. Transformers that have no power losses are called ideal transformers. So the following factors result in power losses, and this is how to limit them. The first way in which power losses occur is through heat losses. So a way to combat this is to use thicker, lower resistance wires. Second one is eddy currents, and you laminate the core. Or hysteresis, where there's a delay in magnetization and demagnetization, you just use a permalloy core. Logic gates are electronic operators that send signals based on satisfied conditions, which means 1 or true, or unsatisfied 0 or false. So it uses a kind of binary language. There are 5 types of gates that you should know for now: a NOT gate, an AND gate, an OR gate, a NAND gate, and a NOR gate. So a NOT gate, this is a symbol here, and if the input is 1, it will invert that signal and turn it into a 0. If the input is 0, the output is going to be 1. NOT gates are also called inverters. AND gates are going to have 2 inputs, at least 2 inputs, and 1 output. This is going to be the symbol here. And what we need are 2 positive inputs in order to get a positive output. So if 0 and 0 gives a 0, 0 and 1 gives a 0, 1 and a 0 gives a 0, but a 1 and a 1 would give a 1. An example of this would be username and password systems, where 1 would be a username and 2 would be a password, and the output would be your ability to log into whatever you want to log into. An OR gate means that at least one of the inputs has to be positive in order to get a positive output. So only one of these has to be 1 in order to get a positive output, at least one. So 0 and a 0 would give you a 0. 0 and a 1 would give you a 1 because there's at least 1. 1 and a 0 would give you a 1. And if both of them are 1, the output is going to be 1. So an example of this would be burglar alarm systems, where you would have a burglar alarm installed on your windows and your doors, and only one of the doors or one of the windows has to be broken for the alarm to go off. If it was an AND gate instead, the burglar would have to break all of the windows and all of the doors in order for the alarm to go off. Now, NAND and NOR gates are very similar to AND and OR gates. The only difference is that you just do the opposite. So you have to imagine for a NAND gate that it passes through an AND gate and then a NOT gate. So basically the NAND and the NOR, the N, the first N means NOT. So NAND means not AND and NOR means not OR. So all you have to do is do the opposite. So for an AND gate, 0 and a 0 would usually give you a 0, but you flip it and you get a 1. 0 and a 1 would usually give a 0, but now you get a 1. 1 and a 0 would usually give you a 0, now you get a 1, and 1 and a 1 would usually get a 1, but now you get a 0. You do the same thing with the NOR gate, where the only negative output would have been 0 and 0, but in this case here you get a 1. Here's a logic gate problem to solve. We have a 1 and a 0 going through an OR gate, and we have a 1 going through a NOT gate. And you are going to figure out what is going to be the inputs at D, E, and what is going to be the output at F. Pause the video and see if you can figure it out. If you did it correctly, this would have been your answer. This was an OR gate, so 1 and a 0, you'll get a 1 coming out of it. This is a NOT gate, so a 1 would result in a 0. And this AND gate here, this 1 and a 0 would result in a 0. Here's one more that you can solve. Pause the video and see if you can figure it out. This is what you'll get if you did it correctly. This 1 and this 1 goes through this OR gate and you get a 1. This 1 and this 1 goes through a NOR gate and you get a 0. This 1 and this 0 goes through a NAND gate and you get a 1. These are the particles within an atom. These are the ones that you have to know. We have the proton, neutron, and electron. The mass of a proton is 1. The mass of a neutron is 1. The mass of an electron is given as 0. The charge of a proton is positive 1, the charge of a neutron is 0, the charge of an electron is negative 1. The founder of the proton is Ernest Rutherford, the founder of the neutron is James Chadwick, the founder of the electron is J.J. Thomson, who also came up with the plum pudding model, which is not used today. Here we have the Bohr model of the atom, and in the middle here we have the nucleus, which contains nucleons, which are basically protons and neutrons, and they are held together by the strong nuclear forces. Electrons, which are held in orbits by weak nuclear forces, orbit or go around the nucleus as seen here. In this particular carbon atom, we have 6 protons, 6 neutrons, and 6 electrons. Keep in mind here that the first shell can only hold 2 electrons, the second shell can hold 8. The atomic number is the number of protons in the atom. In this case here, the atomic number is 6 because there are 6 protons. The mass number is the number of protons and neutrons in the atom. In this case here, the mass number is 12 because 6 plus 6 is 12. How do we know that the atom looks like that? Well, this is because of the Rutherford gold foil experiment. Basically what happened here is that a source fired a stream of positive alpha particles through a thin slice of gold foil. Why gold? Because gold was very malleable and could have been sliced very, very thin. A detector strip of zinc sulfide illuminates in the spots where the particles collide. It lights up. Only the particles that hit or come close to a gold nucleus are deflected. Most of them don't, and thus most of them actually just pass through the foil without being deflected. So the scientists who did this experiment are Geiger, Marsden, and Rutherford. Now if you take a closer look here, these orange circles represent gold nuclei and these represent alpha particles. We have 3 pathways here, A, B, and C. Now pathway A here, particle A, we can see that it bends or it gets deflected just slightly. This is because it came close to a nucleus and was deflected by a small angle. This is because alpha particles are positive and the nucleus is also positive, so they would repel. B doesn't even come close to a nucleus, so this is undeflected. It keeps traveling in a straight line. And C collided head on with a nucleus and was greatly deflected. Basically it hit here and it bounced back like that. Here we can see a list of observations and interpretations for the gold foil experiment. Here we can see that most of the alpha particles travel through the foil undeflected, and the interpretation is because most of the atom is actually empty space. Some alpha particles are deflected by small angles. This is because the nucleus is positively charged, as is the alpha particle. And occasionally one of them would be deflected right back, and this is because the nucleus carries most of the atom's mass, so it basically hits, action, reaction, bounces back like that there. Now if you want to know how big a nucleus is, imagine a grape or a marble in the middle of a stadium. The stadium is the atom, the grape in the middle of it is the nucleus. That is how small it is. Isotopes are atoms of the same element which have the same atomic number but different mass number. This means that they have the same number of protons but different number of neutrons. For example, here we have carbon 12, which has 6 protons and 6 neutrons. Carbon 13 has 6 protons but 7 neutrons, and carbon 14 has 6 protons but 8 neutrons. Here we have various uses of radioisotopes. Feel free to pause the video and take note of them. We should know at least one of them from each field, and we should know the use for that particular isotope. Radioactive decay is spontaneous and random and occurs when a nucleus gets far from a 1 proton to 1 neutron ratio. So for example, here carbon 12 has 6 protons and 6 neutrons. That is an exact 1-to-1 ratio. That would be stable. Carbon 13 is also stable because it has 6 protons and 7 neutrons. That is still within the relative range. But carbon 14 on the other hand has 6 protons and 8 neutrons. That is getting a little further away from 1 proton to 1 neutron ratio. That means that carbon 14 is unstable, and what's going to happen is going to undergo radioactive decay. It's going to lose mass over time, and it's going to release radioactive particles called alpha, beta, and gamma radiation. So the 3 types of radiation are alpha particles, beta particles, and gamma rays. Alpha particles, as you can see here, are helium nuclei, basically 2 protons and 2 neutrons. The symbol for alpha particle is written here. Beta particles are fast-moving electrons. This is a beta particle, and this is the symbol is written here, which has a mass of 0 and a charge of -1. Gamma rays are high-frequency electromagnetic waves. The differences between the different types of radiation. Well, alpha particles are the least penetrating, the most ionizing, they are stopped by paper, and they have the lowest range. Beta particles are intermediate in all these characteristics, and they are stopped by aluminium. Gamma rays are the most penetrating, the least ionizing, and they are stopped by lead, and they have the most range. Once again, alpha particles are stopped by paper. Beta particles can penetrate paper but are stopped by aluminium. Gamma rays can penetrate paper, aluminium, but are stopped by lead. Cloud chambers are sealed dishes filled with alcohol or vapors that show the trails of radiation emissions. This is an easy way to tell what type of radiation is being emitted from a source. Alpha particles show up as thick trails, beta particles have thinner, more jagged trails, and gamma rays typically show up as little scattered spots in the petri dish. So in electric fields, positive alpha particles are deflected towards the negative plate. As you can see here, alpha particles are heavier and thus they take a little more time to be deflected than beta particles, which are lighter. Here we can see the positive going towards the negative. Negative beta particles deflect towards the positive plate in which you are seeing here. And gamma rays are neutral, they don't have a charge, so they remain undeflected, what you are seeing here. They don't go either towards the positive or the negative. So in order to tell the direction of radiation in magnetic fields, you have to use Fleming's left-hand rule. Remember, beta particles are electrons, so those are considered a current. So beta particles would move to the right, and they are deflected more than alpha because they weigh less. Alpha would go in the opposite direction to beta, and gamma, since it has no charge, remains undeflected. So in order to tell this, what you'd have to do is, for Fleming's left-hand rule, have your thumb being pointed up to show the thrust. Your index finger or your feel finger is going into the screen, and thus your middle finger or your second finger is pointing to the right, and that would be the direction of the current. Radiation safety. Now, after Marie Curie, who discovered radium, succumbed to radiation-related disease because she was handling most of it with her bare hands, safety precautions were introduced. This included storing radioactive materials in lead containers, wearing safety gloves or using forceps when handling radioactive materials, staying behind protective screens when necessary, wearing hazmat suits in irradiated environments, as what you are seeing on your right here. During radioactive decay, you have alpha decay, beta decay, and gamma decay. We are only going to go into alpha and beta. During the decay of uranium-238, we can see that there are 2 protons and 2 neutrons leaving the uranium nucleus here. This is turning the uranium into thorium. And here we can see the equation here. Uranium turns into thorium after losing a helium nucleus, so basically an alpha particle. So the atomic number decreases by 2, and the mass number decreases by 4. You can see this here. 238 minus 4 is 234. 92 minus 2 is 90. Here we can see beta decay of thorium-234. Basically what's happening here is that a neutron is becoming a proton, and the atomic number raises by 1. The mass is unaffected as a result. So if we look here, we can see thorium-234-90 is losing a beta particle, and the mass doesn't change as it turns into Pa protactinium. 234 is still 234, but the 90 raises by 1 and becomes 91. This is because a neutron is turning into a proton, so the atomic number raises by 1. This is how decay equations are written. Take a look at them, pause the video. Is basically the same things that we looked at before. Half-life is the time taken for a radioactive substance to decay by half. So for example, if we have iodine-131, which is an unstable isotope, this has a half-life of 8 days. So if there were 1,000 atoms of iodine-131, after 8 days there would only be 500 atoms, half the amount. And after another 8 days there would be only 250 atoms, which would be half of 500. So every 8 days the substance or the isotope decays by half. Here we have the first worked example. An 800 milligram sample of radon decays over a period of 20 days until only 25 milligrams remains. So we went from 80 milligrams to 25 milligrams in 20 days. What is the half-life of radon in days? So what we have to do is start with how much mass we had at first, which is 800. After our first half-life depicted by this arrow, there will be 400, half of 800. After the second half-life, there will be 200, then 100, then 50, then 25. If we want to count the number of half-lives, all we have to do is count the number of times we halved this amount, which means the number of arrows. So we have 1, 2, 3, 4, 5 arrows. So the number of half-lives is 5. So if 5 half-lives were equal to 20 days, one half-life would be 20 days divided by 5, which is 4 days. So each one here represents 4 days. This would be 4 days, 8 days, 12 days, 16 days, 20 days. This here is our second worked example. If iodine 131 has a half-life of 8 days, how many days must pass before it reaches 1/16th of its mass? So once again, we start with our full number. In this case here, we don't have a number for the mass, but we start with the whole, which is 1. After one half-life, we will have a half of the amount. After another half-life, we will have a quarter, then 1/8, then 1/16th. You count the number of arrows, and that will tell you the number of half-lives. That will be 1, 2, 3, 4. The number of half-lives will be 4. The half-life, which is the time that it would take to decay by half, is 8 days. So to find the time elapsed, we will have to say 4 half-lives by 8 days, and that is 32 days would have passed as a result. This is a half-life graph. So how you figure out half-life from this graph, after you draw it, you'll see that basically is a curve that goes down like this. You pick any number from the graph, and you must choose a pair, but the second half of that pair must be half of your first number. So for example, my first number is going to be 80. So that means my second number of that pair is going to be half of 80, which is going to be 40. So for example, if I pick 20 as my first number, my second number has to be half of that, which will be 10 in this case. This could be any number you can start with. So you can start with 60, but your second number would have to be 30. If you start with 50, your second number should be 25, which will be half. So in this case here, what we are trying to see is the rate of decay, or how many counts per minute. How long does it take to halve? So if we start with 80 counts per minute, that is the rate of decay in this case, and we're going to label that T1, and that is 0 days in, as what you see here. Now, the time taken for it to drop from 80 to 40 in this case T2, this will take 2 days. So this will be the half-life. We've already solved it, but because half-life is random and sort of spontaneous, what we have to do is not just take one pair of values, we'll take 2. So my second pair, I took 20 and 10, which will be T3 and T4 in this case. So 20, as we see here, this is going to be 4 days in, and 10 is going to be 6 days in. The difference between these two numbers, 6 minus 4, this would have been 2 days would have passed here as well. So once again, we get the same number, but we still write our working. So our first half-life will be T2 minus T1, which is 2 minus 0, which is 2 days. Our second half-life is going to be T4 minus T3, which is 6 minus 4, which is 2 days. So typically what you'll get is these two numbers ending up slightly differently, and you'll find the average between the two. In this case, we have the same thing, but if you have them different, you find the average. So for example, if this was 3 days and this was 2 days, you say 3 plus 2 is 5, divided by 2 is 2.5. In terms of nuclear energy, we have fission reactions and fusion reactions. In fission reactions, which typically occur in nuclear reactors, we have one large atom splitting into 2 or more smaller atoms. In a fusion reaction, you would have 2 smaller or lighter atoms joining to form a larger one. Fusion reactions occur in the sun all the time, where hydrogens fuse to form heliums. In terms of nuclear energy and nuclear reactors, we have to list 2 pros and 2 cons. The pros are this: one, it is more efficient than fossil fuels and yields much more usable electrical energy. There's less waste as heat and things like that. The second pro is that it produces no greenhouse gases. It does not contribute to climate change as a result. The two cons would be: one, there's a risk of nuclear meltdown. We've seen this happen in Chernobyl in the USSR. We've also seen it happen in Fukushima in Japan. Two, radioactive waste is very difficult to dispose of. Basically, you have to bury it in lead containers, which can get kind of expensive. If you have to calculate nuclear energy, we use this formula here: E is equal to mc squared, where E is energy, m is mass, and c is the speed of light, so c squared is the speed of light squared. Remember, the speed of light is given as 3 by 10 to the power 8. What if we had to calculate the energy released in a nuclear reaction? Let's look at this equation here. Here we have two hydrogen isotopes. Hydrogen 2 plus hydrogen 3 gives you helium, a neutron, and some energy. On the table to the right, we can see that we have some atomic masses given in a unit called U. And hydrogen 2 is 2.014, hydrogen 3 is 3.016, the helium is 4.003, and the neutron is 1.009. Now we're going to see each unit U, which is not a standard unit, is equal to 1.66 by 10 to the power negative 27 kilograms. Don't worry about that too much right now. So what we're going to do is we're going to calculate the energy released in the reaction above. This is how we do it step by step. First, they're going to add the masses on the left. So we have hydrogen 2 and hydrogen 3. We're going to add these two numbers here. So 2.014 plus 3.016 is equal to 5.03U. That is our first step. Our second step is that we're going to add the masses to the right of the equation. So this is going to be helium plus the neutron. And this will be 4.003 plus 1.009. And that's 5.012 units U. Now you're going to notice that this number on the right, 5.012, is a little less than what we got on the left, 5.03U. Now this is because the remainder of the mass was converted into energy, as E is equal to mc squared. So the difference in mass is actually what's going to convert to the energy there. So what we have to do next is to subtract the difference. So we're going to see 5.03 minus 5.012. So the difference here, delta M, is going to be equal to 0.018U. The problem is that unit U is not used in physics really. We need to convert it to kilograms. So how do we do that? Well, that's pretty easy. We're going to have to multiply this 0.018U by 1.66 by 10 to the power negative 27. So when we do that there, when we multiply it, we are going to get this number here, 2.988 by 10 to the power negative 29 kilograms. Finally, we're going to use Einstein's formula to calculate the energy E. So you're going to say delta E is equal to delta mc squared. Now remember, c is the speed of light, which is 3 by 10 to the power 8 meters per second. So c squared is basically going to be this number squared. So 3 squared is 9 and 10 to the power 8 squared is 10 to the power 16. So we're going to multiply delta M, which is what we would have obtained before, multiply by 9 by 10 to the power 16, and our answer here is going to be 2.6892 by 10 to the power negative 12 joules. And that's it. That's the whole syllabus. You all take care and good luck.